Yeah, you could be the great.
Hi, welcome to DSA. On today's episode, we are going to be looking at how you can crack redox reactions. All right, if this is your first time coming across our videos, this is Learn with DSA. We are an educational platform. Please subscribe to our YouTube channel, follow us on any social media platform where you're watching. And of course, like this video and share with your friends. This is the simple secret to crack redox reactions for 2026 JAMB. All right, let's go. Cracking redox reactions. Of course, what do we mean by redox? You must have been hearing about that and wondering what that means in your textbook. The word redox is an addition of two types of reaction: reduction, oxidation. Okay, and that's how we form the word redox, and that gives us redox. Okay, that's how we came about the word redox reactions. All right. So what do we mean by redox reactions? Before we go on to all of this, we need to first understand what is a reaction. Of course, reaction is just going to be like effects or changes that result from the combination of two or more substances. All right. Now, if that is clear, redox reactions will therefore be effects or changes that follows reduction or oxidation when substances are mixed with one another. All right. If that is also clear, don't forget we're going to be lifting it pieces by pieces. Now we know what or how we came about redox reaction and what reactions in itself actually means. Now the next thing is let's dive deep into the concept of this topic. So redox reactions, we have different kinds of reactions. We have neutralization reaction, which is a reaction between an acid and a base to give us salt and water only. Of course, you know that very well. You know about combustion reactions, that is the burning of substances in the presence of air or oxygen, which may be complete or partial. Now, but all of those types of reactions aside, the one that concerns us now is we also have reduction oxidation reactions. So what are reduction oxidation reactions? We are going to be looking at different bases for the definition of reduction oxidation reactions. So we're going to start with the first one, number one, based on or let's use terms. Okay, in terms of oxygen. All right, in terms of oxygen, we say that reduction is the removal of oxygen, while oxidation is going to be, like you guessed right, addition of oxygen. Okay, redox in terms of oxygen, removal of oxygen for your reduction, addition of oxygen for oxidation. I mean, it's oxidation. So you expect that that's going to be what? Favoring oxygen. Okay, that's the first term. We go again. In terms of oxygen, reduction is removal of oxygen. Oxidation is the addition of oxygen. Now, we go down to the second stuff. Number two. Okay, red is removal and ox is addition. Okay, the second basis or term is in terms of hydrogen. In terms of hydrogen. All right, in terms of hydrogen, reduction is addition of hydrogen this time around, not like the opposite of what we have above. And of course, like you expect, oxidation is going to be removal of hydrogen. All right, okay, let me use H instead of H2. So addition of hydrogen, removal of hydrogen. Okay, so number one, in terms of oxygen, reduction is removal of oxygen, oxidation is addition of oxygen. And in terms of hydrogen, reduction is addition of hydrogen, while oxidation is removal of hydrogen. If you know one, you can actually remember the other. It's just opposite of each other. Now, the third one is in terms of electronegative element. Electronegative element. All right. Now, in terms of electronegative elements, before I go on with the definition, what are electronegative elements? All right. Electronegative elements, like you can rightly remember in periodic table, we said electronegativity is the tendency of an element to attract electrons more towards itself. Yeah. Okay. And we mentioned that, first, going by the trend on the periodic table, the most electronegative element is fluorine. I give a simple mnemonic that you always remember. Instead of saying someone is your uncle, you say funkle. So someone is your funkle, put an S. So you call two or more uncles, you call them funkles. All right. Now, what does this represent? This is fluorine. Okay. This is oxygen. This is nitrogen. This is chlorine. This is sulfur. This is decreasing electronegativity on the periodic table. So if you are adding any electronegative element, it can also be a basis or term for the definition of redox reactions. So in terms of electronegative elements, reduction is removal of electronegative elements, while oxidation is addition of electronegative elements. All right. So that's for the definitions that we have in terms of electronegative elements. Okay. The next thing is in terms of electron transfer. Now we are getting into the real deal gradually. In terms of electron transfer, of course, there's a simple mnemonic that is very, very much popular. We say oil rig. Okay. If you are the typical Yoruba person, you say if you're talking or whichever way you want to call it. That's just by the way. So oil rig, what does it stand for? So this mnemonic stands for oxidation, that's the O, is, that's the I, loss, that's the L, and then the RIG, reduction, is gain. So if you're trying to remember the definition for redox in terms of electron transfer, you use oil rig. Oxidation is loss, reduction is gain. What are we talking about in terms of loss here or gain is what? Of electrons. Okay? And now we go to number 5, which is the last and most important one that we're going to look at in terms of oxidation number. In terms of oxidation number. All right. Now, the first thing that comes to mind is what do we mean by oxidation number? Of course, oxidation number is just a conventional value that is assigned to an element to represent the state by which it is binding, maybe in terms of valency to another atom of another element. All right. So in terms of oxidation number, reduction is decrease in oxidation number. Okay. While oxidation is going to be increase in oxidation number. These are the 6 bases or terms for the definition of redox reactions. We are cracking it in it. All right. So the first one in terms of oxygen, reduction, removal, oxidation, addition of oxygen. In terms of hydrogen, we go again, reduction, just the opposite, addition of hydrogen, removal of hydrogen. Rightly. Now you can try, of course, you shouldn't just be looking at me. Try without looking at the video and see if you can remember all of this. Now, the third one in terms of electronegative element, what's that going to be? Of course, you know, that's removal of electronegative element for reduction and for oxidation, addition of electronegative element. Okay, what's the fourth one? Before I mention it, you're right. In terms of electron transfer, we have oil rig. Oil rig, don't forget, which means what? Oxidation is loss of electron and reduction is gain of electron. And the last one, the final, number 5, is in terms of oxidation number. Yeah, you're right. Reduction is just going to be reduction. I mean, you're decreasing the oxidation number, rightly, and oxidation increase in oxidation number. All right. I believe all of that is clear. If you're trying to see if you remember them, pause the video, try to see if you can define these 5 terms without checking into the video. Do that until you can actively recall all of that. All right. Now we move on to the next step of the way. We said that redox reactions can be defined in terms of oxidation number, rightly, and it means that we need to know how to detect or calculate or at least arrive at in order to identify the oxidation number of atoms of elements in any particular reaction. Okay, so that leads us to the following subheading: rules for determining oxidation number. That is, how do you decide or arrive at the oxidation number of a particular atom in an element or a reaction? Of course, everything in life is based on rules. Apparently, even though the biggest rule is breaking rules, but that's by the way. Rules for determining oxidation number. Okay, we're going to learn a couple of them while the other ones we just try to freestyle around them. Okay, number 1, we say that the sum, okay, let's call it algebraic. Yeah, the algebraic sum of the oxidation number, or you can say oxidation states, of elements, okay, in a neutral molecule is 0. All right. So you think about something like, let's look into this. Let's say we have a compound or molecule A2CO3. Okay, this is a molecule or a compound. You think about limestone, CaCO3. You think about H3PO4. All of these are examples of molecules or compounds. Now, according to the number one rule, algebraic sum, why do I call it algebraic sum? Or an algebra is a mathematical equation that is made up of variables and coefficients. Of course, you know your variables are like your alphabet and your coefficients are your numbers, which are your natural integers from 1 to infinity. All right, so we come back here, Na2CO3. This is Na, a variable, which is an alphabet, and then we have 2, which is a coefficient. So when you add everything together, algebraic sum is going to be Na2. Na2 means 2 sodium, so that's 2 times Na plus C plus 3 times O. Everything, this is the algebraic sum, must be equal to 0. Okay, for a neutral molecule. This is neutral because when you look at this molecule, there is no charge. Okay, if you don't know what I mean by charge, there's no big term in that. There are 3 fundamental entities of matter: atoms, molecules, and ions, right? An atom is the smallest part of an element that can take part in a chemical reaction. Molecule is the smallest part of a substance that can exist alone and still retain the individual property of that substance. An ion, which is where I'm going to, ions are formed when an atom is charged, and an ion can be positive or negative. If it is positive, we call that cation. If it is negative, we call it anion. If you want to learn more about that, go and check on the topic matter. Okay, you can preferably use your new school chemistry by Ababio or Lamlat's chemistry. All right, so coming back to this, because this is not ionic, there is no charge, positive or negative, on this molecule. So this is the neutral molecule. All right, so everything is going to be equal to 0. So for this as well, what will be the algebraic sum? You're going to have Ca, because it is 1, plus C1 plus what? 3O. And that's going to be equal to 0. All right, let's do for these two. That's going to be 3 times H plus, what do we have? P plus 4 times O, all equal to 0. All right, so this is the first rule that you have in determining oxidation number. We're going to come back to this later. Now, what's the second rule? The second rule says that, just similar to this, the algebraic sum, same algebraic sum of oxidation number or states of elements in a charged molecule. I started with the neutral one, now I'm going to a charged molecule. In a charged molecule is equal to the charge it carries. Okay, it's equal to the charge it carries. So let's assume that I give you a molecule like H3PO4 loses a proton to form conjugate base. So we're going to have H2PO4 minus. So if we have a molecule like this, the algebraic sum, like we did earlier, is going to be 2 times H plus P plus 4 times O, right? Everything will not be equal to not 0 this time around because there's a charge. What's the charge here? Minus. And that's what? Minus 1. So everything will be equal to minus 1. So if I have something like H3O plus, everything is going to be 3 times H plus O equal to plus 1. Okay? When you have a charged molecule, the algebraic sum of the oxidation numbers is equal to the charge it carries. Now let's keep that outside. Now the next thing we move down to is, we were looking at the sum of all the molecules. Okay, we say Na3PO4 algebraic sum is equal to 0, H3O plus algebraic sum is equal to plus 1. But what will now be the oxidation state of each of the elements that we have in that molecule? What am I saying? Look at Na2CO3. We said everything is equal to 0. That is 2Na plus C plus 3O equal to 0. Now, the big question is, what is the oxidation state of Na? What's the oxidation state of C? What's the oxidation state of O? How do we identify this? Because we cannot have this much amount of unknowns and arrive at an answer. So what we do, or the next rule, is now I'm going to follow that the oxidation state or number of an element in a molecule, okay, or let's say in a compound, is equal, this is just tactical, is equal to, you can say, the valency, That's the most appropriate thing. Or you can say it's equal to the group that it belongs to. You get? You can say the valency, the group. Some even go ahead and say that is equal to the number of unpaired electrons, which is like the bond pair or whatever. But I just think that it's easier to go with the group. It's just, we're going to calculate the oxidation state of oxygen now in this molecule. Say Na2CO3 equal to 0. Okay, so we have that Na is in group 1, so that is 2 times Na, okay, plus C plus 3 times oxygen, everything equal to 0. So sodium group 1, that's 2 times 1, plus carbon is in group 4, that is 4, plus oxygen that we are looking for now. Let's say oxygen is X, that's 3X equal to 0. So this is 2 times 1 is 2, plus 4, plus 3X equal to 0. If I rearrange it, I'm going to have 3X equal to, plus 4 comes to this side, it becomes minus 4. 2 comes here, it becomes minus 2. So everything eventually becomes minus 6. So 3X equal to minus 6. What do? You divide both sides by 3. So X will become minus 2. And that will be the oxidation state of oxygen. Okay? That will be the oxidation state of oxygen. Alright. If we can do that already, let's try to do for another element. Think about doing for, okay, let me give you something like NaCl. I mean, this is very, very easy. So what will it be? What will be the oxidation state of chlorine in this case? I mean, even without calculating, okay, sodium is in, everything is going to be equal to 0, right? So sodium is in group 1, that's plus 1. Chlorine is what we are looking for, X equal to 0. So X will be equal to 0, plus 1 comes here, becomes minus 1. So X is equal to minus 1. Now, I intentionally give you chlorine here because usually, based on my first example, you would want to think that chlorine is in group 7, so you should have oxidation state of plus 7. But like I said earlier, even though we have rules, there is no cut fit principle to anything at all. So the biggest rule is to break the rules. All right. So in that case, it means that some elements do not exactly have oxidation state of the group that they belong to. Now that leads us to the other rules that we're going to learn about. Okay. So now we go to number 4. Rule number 4. We're going to be specific now. So for number 4, we say that the oxidation state of oxygen, oxidation state or number of oxygen is usually minus 2. Okay, it's usually minus 2 in oxides. Okay, however, this is like normal oxides or dioxides. Okay, it's safe to call it dioxides. Now we have other types of oxides where oxidation state will be different for oxygen. Okay, it is minus 2 in dioxides, it is minus 1 in peroxides, and minus half in superoxides. Okay, so let's try to look at examples of these stuff we're talking about. Okay, for oxide to talk about Na2O. Okay, so you know everything is going to be equal to 0. Sodium is plus 1 times 2, that's plus 2 equal to plus 2 plus X equal to 0. So X will eventually become minus 2. Normal oxides. Okay, when you are doing oxygen in compounds like, just like Na2CO3 that we did earlier, we got oxygen to be minus 2. So usually, when you come across oxygen in common compounds or molecules, the oxidation state of oxygen will always be what? Minus 2. Never forget that. Okay, now, but we said in peroxide, it will be minus 1. What's an example of a peroxide? You think about H2O2, think about Na2O2. Okay, this is sodium peroxide, this is hydrogen peroxide. The oxidation state of oxygen here is minus 1. Let's find out. So hydrogen is plus 1 times 2. Oxygen is X, 2X, right? Equal to 0. So 2X will eventually be, when plus 2 comes here, it becomes minus 2. Divide both sides by 2, X will be equal to what? Minus 1. So whenever you have oxygen in a peroxide, 2, 2, 2, 2, you're going to find out that oxygen will always be what? Minus 1. Alright, what's an example of a superoxide? Superoxides are majorly formed by potassium and rubidium. So we have a potassium superoxide, KO2, and rubidium superoxide, RbO2. So let's find out what's the oxidation state of oxygen here. So potassium is the plus 1, oxygen is 2x, because we are looking for that. Everything is equal to 0. So when 1 comes to this side, it becomes 2x equal to minus 1. Divide both sides by 2, x becomes minus half. All right. So in superoxide like potassium superoxide and rubidium superoxide, oxidation state of oxygen is always minus half. Right. Now we move down to the next one. We are done with oxygen. Number 5. This is supposed to come before number 4, but still good to go. The oxidation state or number of any element in its stable state is equal to 0. Okay? When you have an element in its stable state, the oxidation state is equal to 0. You think about elements. What are examples of elements? You know your first 20 elements. Hydrogen. Okay? If we start with hydrogen, the stable state of hydrogen is usually as diatomic hydrogen molecule. What I'm saying there is H2. Diatomic means 2 atoms. This is H2, hydrogen, hydrogen. All right. So the oxidation state of hydrogen here will be equal to 0. What's the stable state of sodium? Sodium is stable as just Na. So if you have just Na and they say what's the oxidation state, it's going to be what? 0. Noble gases like helium is stable as He. What's the oxidation state? 0. If you have something like fluorine, stable state is F2. What's the oxidation state? 0. So any element in a stable state has oxidation state equal to 0. Never miss that 2. Now we move down as well to other exceptional cases. Rule number 6 now. The oxidation state of hydrogen is usually +1. Okay, it's usually +1 except in metallic hydrides. Except in metallic hydrides where it is what? -1. Except in metallic hydrides where it is -1. So what's a metallic hydride? Where hydrogen is directly bonded to a metallic atom. Think about stuff like AlH3, okay, and NaH, the likes of them, LiH, and so on. So the oxidation state of hydrogen in this case is going to be -1. Anytime you have a metallic hydride, hydrogen is always -1. Okay. Now, you think about the most popular question that attracts this rule is, what is the name of the compound? What's the alpha name of the compound? NaAlH4. Okay. So this is in your past question. And you know that, of course, this is going to be equal to 0. So sodium is going to be +1. Aluminum belonging to group 3 +3. Hydrogen, you call that minus. Okay, let's call that plus x. But we have 4 of it. So that's 4x equal to 0. So this is going to be +1 +3. That's going to be +4 plus 4x equal to 0. So 4x is equal to what? -4. You divide both sides by 4. X will be equal to what? -1. Okay? So hydrogen is -1. Now, the question in your past question is, what is the opaque name of this compound? Don't forget, aluminum is what? 3. So the usual simple way to name your compound, you say this is sodium tetra, means 4. Tetrahydrido, because it's a prefix. Sodium tetrahydrido aluminate, that's a suffix, aluminate 3, because the oxidation state of aluminum is 3. So it tells you that there's even a relevance to know the oxidation state. It can help your nomenclature of compounds. So again, this is sodium tetrahydrido aluminate 3. All right, we leave that. Done with hydrogen. We've taken oxygen as well. Now, there are some other elements too that we need to pay attention to. That important one is fluorine. Okay, the oxidation state of fluorine is always -1. The oxidation state of fluorine is always -1. But there's an exception, except in HOF, where it is +1. So if they give you a compound, you don't need to calculate. Once it is fluorine, it will always be what? -1. Other elements will readjust their own state to fit up, making up fluorine has oxidation state of -1. In HOF, it is +1. So if I say, what's the oxidation state of fluorine in OF2? You don't need to do any calculation. Fluorine will always be what? -1. Never make that mistake. All right. We've been able to write out the common oxidation states that we need to know. Now, you should know that elements may have variable or different oxidation states depending on the element that they are combining with or the number of unpaired electrons. So if we know the rules already for calculating oxidation number, let's try to see some examples that can help us navigate questions in the 2026 JAMB or WAEC or NECO, whatsoever exam it is that you want to do. So let's say we are looking for the oxidation state of carbon, okay, in CaCO3. All right, this is going to become CaCO3 equal to what? 0. Okay, and therefore calcium is in group 2. That's going to be 2 plus carbon X, oxygen minus 2 times 3. Okay, don't forget oxygen is here as an oxide, so it's going to be minus 2. Everything equal to 0. This is minus 6. This is X. This is 2. So eventually you're going to have X equal to minus 6 become plus 6. 2 becomes minus 2. So X is equal to plus 4. So we say that this compound is calcium trioxocarbonate what? 4. Calcium trioxocarbonate 4. And that way we've been able to name that compound. So you're going to have your own exercise to do because we cannot solve all of the examples that we have in this video. So do this and show me your own answer in the comment section. What is the oxidation state of copper in CuIO32? Okay, of course, give your look at it. We're going to have corrections to that. Okay, and we have another one. What's the oxidation state of phosphorus in Na3PO4? Okay, let's do with that too, and we call it a day there. Okay, that's where we're going to pause for calculating oxidation number. I also wanted to give you an example on ions. Okay, so let's say we're having a hexacyanoferrate, FeCN6. Okay, raised to power 3 minus. This is a complex ion. Okay, we want to get the oxidation state of ion here now. You're going to have that Fe is unknown, X plus. Now, this is a molecule, a radical rather, Cn. Cn has oxidation state of -1. You can check in your textbook for radicals. But we have 6 of these radicals, so that's -1 times 6 equal to what? -3. Don't forget, it must be equal to the charge. So eventually, you're going to get X minus 6 equal to -3. And that will be X equal to -3 plus 6, which is what? Plus 3. So this is going to be hexacyano. Hexa is 6. Hexacyanoferrate 3. Hexacyanoferrate 3. All right, so attempt the two that you have here as your exercise and tell what your answer is in the comment section. I'll be checking it and we'll make proper corrections if you do not get it. All right, that's for calculating oxidation number. The next thing we need to do now is how do we identify oxidizing and reducing agents? Okay, how we came about the idea of oxidizing and reducing agents is that we're talking about redox reactions. And of course, for us to have any change, we say popularly that change begins with you and my very self. Okay, so in this case, the change, that is redox reactions, is going to happen when there is one person that is ready to reduce and another person that is ready to oxidize. Are you ready? Yeah, let's go. So when we talk about redox reactions, we cannot do without mentioning reducing agent and oxidizing agent. So the reducing agent is just like saying somebody is an OPay agent. What would an OPay agent do if they see you? Of course, they will open an OPay account for you. When you see an MTN agent will open an MTN account for you. So if you see a reducing agent, what will it do for you? If it's opening an account, it will open a reducing agent account for you. Do you get? All right, but that is just by the way. So when we say reducing agent, what they simply do is that they reduce anything they come in contact with in a redox reaction. Okay? Reducing agent, what do they do? Reduction. To others. Oxidizing agent, what would they do? Oxidation to others. Oxidizing agent, oxidize other species. Reducing agent, reduce other species. I think that's pretty easy to remember. Now, but you must now think about what will be the effect on them. You know, we should not look at that with respect to OPay agents. I mean, some OPay agents opening OPay accounts for you. You may find them using First Bank, using Money Points. Some people even using Kuda, using PalmPay. So you want to send money to them, they give you PalmPay accounts, but they're opening OPay accounts for you. You get? It's just like MTN owning hotspots using Airtel SIM, but that's not our concern. So let's go back to our own business. So reducing agents, they will reduce others, but they themselves, they cannot be reduced. That's the irony of it. So it's a paradox. So reducing agents, they reduce others, but themselves, they are what? They are oxidized. All right? Reducing agents reduce others, themselves are what? Oxidized. Now you can guess right. Oxidizing agents, they will what? They will oxidize other people, but themselves will be what? Reduced. Very easy. cheap and good to go. Okay, so again, reducing agents reduce others and themselves are oxidized. Oxidizing agents oxidize others, they themselves they are reduced. Okay, now you must also know that reducing agents are otherwise called reductants. Reducing agents are otherwise called reductants, and oxidizing agents are otherwise called oxidants. Okay, reducing agents, reductants, oxidizing agents, oxidants. Okay, now that we know that concept, the next thing is to be able to identify reducing agents and oxidizing agents. Before we go down to the identification part, which is going to be the last segment of this video, we should know about some common oxidizing and reducing agents. So let's start with the reducing agents. We think about substances like coke. That's the first major reducing agent that comes to mind. And you know that coke is what? Almost, about 99% carbon. So coke is carbon. So you may see coke or carbon. That's like the first reducing agent that comes to my mind. Okay, think about another thing like CO, carbon monoxide, or carbon 2 oxide, whichever way you want to call it, CO. Okay, you think about something like graphite, of course, that's still coke. You think about something like HCl, okay? You think about something like ammonia. You think about something like sodamide, which is NaH2. And of course, generally, all metals are reducing agents. Metals are generally reducing agents. Of course, you can also think about your NaAlH4, NaBH4, tetrahydroborate, and tetrahydroaluminate 3. They are both reducing agents. Of course, now there's also something that you should note is that when we have elements that have variable oxidation state, the lower oxidation state of that element is going to be a reducing agent, while the higher oxidation state will be an oxidizing agent. I'm taking that again. When you have an element that have more than one oxidation state, the lower oxidation state will be what? Reducing agent. The lower one is reducing agent. The higher one is oxidizing agent. We can look at it as the person that is below wants other people to what? To come down. They want them to be reduced. So because it is low, it wants others to also what? Reducing agent. Okay? Now, you think about a typical example of that is carbon. Carbon can have two oxides, carbon 2 oxide CO and carbon 4 oxide CO2. The state of carbon is +2 and +4 here. So if you look at CO is a reducing agent, lower state. CO2 +4 is oxidizing agent. Think about something like SO2 and SO3. This is sulfur. Sulfur here is +4, sulfur 4. Here is +6. SO3 is an oxidizing agent. SO2 is a reducing agent. Of course, you know that sulfur has more than these two oxidation states. You can have sulfur as H2S, where oxidation state is -2. You can have sulfur as ordinary S, where oxidation state is what? 0, S8. You can have SO2 where it is +4. You can have SO3 where it is +6. SO3 will form H2SO4. So it's still the same thing. So we have 4 different oxidation states. That is why they say that SO2 can be both oxidizing and reducing agents. Yes, because if SO2 should see H2S or S8, those lower ones will be reducing agents. SO2 will be what? Oxidizing agents, because it is now the senior brother, senior oxidation state. And if it comes across stuffs like SO3, SO2 is lower now. So it will be the what? Reducing agent. SO3 will be oxidizing agent. So there's no big deal about identifying these things. Okay, we've learned about some of the reducing agents. Let's look at some of the common oxidizing agents. Of course, the first oxidizing agent that should come to your mind is oxygen. Meanwhile, hydrogen, don't forget, hydrogen is also going to be a reducing agent. So oxygen is an oxidizing agent. Okay, so oxygen is the first oxidizing agent that comes to your mind. Then you think about other things like H2SO4, like I rightly mentioned, because it's the highest oxidation state, so it will always be an oxidizing agent. All right, H2SO4. Think about other stuffs like acidified KMNO4, which is KMNO4, tetraoxomanganate 7, potassium tetraoxomanganate 7. Think about K2CR207, that's your potassium heptaoxodichromate 6. Okay, you think about other things as well, like your non-metals. Generally, non-metals are oxidizing agents. You think about stuffs like okay, let me think about other example. Okay, like your CO2, of course, CO2 is going to be an oxidizing agent. And when, of course, like I mentioned, when you have elements with variable oxidation state, the higher oxidation state is going to be an oxidizing agent. I would advise that you check more examples, as I cannot exhaust the list in this video. You can go and check your past questions for the common examples, or even check your textbook, which is the best thing to do. We are not doing AI chemistry. While you may get answers, you may not get the ones that you'll be asked in your exam. So please go to your textbooks and check examples of oxidizing and reducing agents. Okay, now we know about oxidizing and reducing agents, which are also called oxidants and reductants. How do you identify them in equations? Okay, how to identify oxidants and reductants in equation is pretty easy. So I'm going to give one or two examples, and then you go ahead and find out more and revert to us in the comment section. So let's start with this first example. I have, okay, let me say I have zinc plus HCl to give me ZnCl2 plus H2. Okay, if I balance this, I'm going to get it like this. All right. So once you identify which one is oxidizing, which one is reducing, the first and one of the common questions that you find in your past question as well is that which of these is not a redox reaction? I'll use this same question to answer the two. We'll use a stone to kill two birds. So this is zinc that is being oxidized by HCl to become zinc chloride and hydrogen gas. Okay, so what we do is we first check the oxidation number. If it is a redox reaction, how you identify that it's a redox reaction is that there must be a change in oxidation number. One must be increased or decreased, whichever way. There must be a change in oxidation number. So we look at zinc. Zinc is in its stable state as Zn. That's the stable state. And remember, according to the rules, when an element is in its stable state, the oxidation state is what? Of course, 0. So in this case, zinc is going to be 0. Okay. Hydrogen usually is what? +1, except in metallic hydride where it is -1. So in this case, hydrogen would what? +1. And if hydrogen is +1, chlorine will definitely be -1. Okay? And then you come here, zinc, in this case, if we try to check for zinc, let's say we don't even know zinc. We know that chlorine is -1. -1 times 2 is -2. -2 equal to 0. Okay? And zinc is x. X minus 2 equal to 0. When -2 crosses to that side, it becomes +2. So zinc is +2. Chlorine is what? -1. Hydrogen is in a stable state. That's what? 0. All right. So in this case, we are trying to now check, did the oxidation number increase or decrease? This is zinc. It was 0 here. Later here, it changed to +2. So let's trace that out. So for zinc, 0 to +2, is that an increase or decrease in oxidation number? Definitely an increase. Whenever you have increase in oxidation number, according to definitions, it is what? Oxidation. Pretty easy. Okay. And then this is HCl. Hydrogen is what? +1. Chlorine is -1. Chlorine did not change. Hydrogen changed from +1 to 0. Is that an increase or decrease? Definitely a decrease. So we draw that out. Another arrow. We say that this is what? Reduction. All right. So that is on identifying your oxidation and reduction in this equation. So we look at another example. Combustion of methane, that's CH4 plus oxygen to give us CO2 and H2O. To balance it, we need this. Now I want to check if this is a redox reaction or otherwise. So you say carbon, of course, +4 +1. This is going to be my oxygen in a stable state is going to be 0. So carbon here is carbon 4, still +4. Oxygen here is -2. Hydrogen is +1. Oxygen is -2. So we check. Carbon here, +4 +4. Hydrogen +1. Oxygen 0, -2. Okay, let's check. Maybe we have an error. Okay, I think here, carbon is going to be -4, not +4. Let's check it together. Let's say carbon is x. Hydrogen is 1 times 4. Everything equals to 0. So x plus 4 equals to 0. X equals to -4. So carbon here is -4. If we check here, x plus -2 times 2 equals to 0. So x minus 4 equals to 0. X equals to +4. So now we have the oxidation states of each of them calculated. So the next thing we move down to is check if it is a redox reaction. From -4 to +4, that's an increase. So that is oxidation. Okay, +1 +1, no. 0 to -2, that's a decrease in oxidation number, so that's reduction. All right. So like I mentioned earlier, if you remove any of them out separately, that's half equation. So our oxidation half equation will be CH4 to what? To CO2. And our reduction half equation will be 2O2 to H2O. Okay? So try as much as possible to be able to identify half equations. And like I mentioned, if you want to balance this equation, go to our YouTube channel. You see the explicit explanation of how to balance redox reactions in one of the videos on our YouTube page. All right. So how do you identify the reducing agent, the oxidizing agent? We say that the reducing agent will do reduction to the other species. So reduction is happening to this person. That means it was caused by CH4. So in this case, we say that CH4 is the what? Reducing agent, because it's the one that does reduction to oxygen. Okay? And oxygen, what does it do? It is making oxidation happen to CH4. So we say that oxygen is the oxidizing agent, which is also called oxidant. Reducing agent, which is also called reductant. All right, so that's where we have to call it a stop in this video. I will have to give you some examples to try on your own, while you also check, most importantly, your laminate chemistry and your past questions for further examples. So please do this, and I will be checking your answers in the comment section of this video. Identify, number one, the reducing agent or reductant. Okay. Number two, the oxidizing agent or oxidant. Number three, the oxidation half equation. And number four, the reduction half equation. All right, so we are identifying four things in this equation. Okay, the equation is SO2 plus O2 to give us SO3. All right, let me balance it up for you. So you have to take this as your own exercise and type your half equations in each case in the comment section. All right, that will be all under cracking redox reactions. And I believe that with this that we've done, if you come across any question in redox in your 2026 JAMB or any O-level exams that you are preparing for, you should be able to easily ace it without flinching or blinking twice. All right, that will be all for this episode of the video. Watch out for the next video on our channel. Like I said at the start, if this is your first time, please subscribe to our channel or follow us on whatever social media platform you are viewing this video. And of course, like this video to encourage us and share it with your friends. So I'll see you in my next video. Thank you for viewing.